Welcome to AP Podcast 11.4. This is on the vapor pressure of solutions. Now, we've been spending a little time with solutions. We've talked about the different ways to measure their concentration. We've talked about their solubility. We've talked about the heat of solution and the factors that affect that solubility. Well, here's another scenario that occurs, and that's when you add a non-volatile solvent. A non-volatile solvent. It's going to lower the vapor pressure. If you remember in Chapter 10, we talked about how these molecules will escape a liquid, right? And they will create a vapor pressure. And it's usually very low. But it turns out if you can add some non-volatile, now remember that word non-volatile just means that it's not giving off vapors. If you can add some particles to that solution, it causes the vapor pressure to lower. In other words, let's say these arrows are some kind of magnitude by having big arrows. Well, if I put a bunch of, let's see if I can do this, a bunch of yellow particles in here. Oh, that doesn't work at all. But imagine there's some particles in there. It's going to cause these arrows to be a little shorter. Okay. In other words, adding particles decreases the amount of escapability of the liquid particles to go to a gas. Now, why is that? Well, there's a couple ideas, all right? Somehow, some way, this is causing these particles a challenge to overcome the force, that's going on with the solvent and the solute. Somehow that's working out. Whether it's they're blocking at the surface, that's not a very good reason. But somehow these particles are having a more difficult time escaping. Probably the best way of thinking about it is the entropy. Right? Remember good old S? The disorder. Okay, when I have particles in here, that gives us positive disorder, and positive disorder leads to negative G, right? And we know that when G is negative, reactions and processes are favorable. So that's probably the best way to go about it. Now, as far as answering AP questions, if you just understand this part right here about non-volatile solvents lower the vapor pressure, usually that's as in-depth as they're going. And this process right here, I barely have a grasp of it, and it's tough to understand it, but you just need to understand that liquid is, that vapor pressure is lowering when you add those particles. Now, we can, of course, do some calculating to figure out exactly how much it's lowering, and we use Raoults Law. And unlike Henry's law, this is a law that gets used quite a bit. And so all we do is we take if you want to know the pressure of the solution, you just take the mole fraction of the solvent, okay, there's that mole fraction thing again showing up, times the pressure of the solvent. And it ends up being a relatively trivial calculation. And we're going to practice a couple. There's a few points that are important, though. It applies only to an ideal solution where the solute doesn't contribute to the vapor pressure. In other words, we have to have a non-volatile component, right? And the nice thing about AP is generally this is our situation. We keep things ideal. All right. For those of you that get further in chemistry, you'll get the joy of doing those tougher problems where you're dealing with non-ideal solutions. Right? And then look at this last bullet, because I put this question here because I want you to think about this for a second. Ionic compounds have nearly 2 or 3 more times the vapor pressure lowering than non-ionic compounds. So why is that? Pause the video. Think about it. Did you do it? Well, here's the deal. Think about a good old sodium chloride. Oops. Let me try this again. Sodium chloride ion, right? What happens when I dump that in a solvent? Well, I get some of this, and I get some of that, right? I get a 2 for 1 number of particles. And this really has to do with just the number of particles. So for every 1 mole of sodium chloride, I get 2 moles of ions. And so that's why you get this 2 or 3 more times. How would you get 3 more? Well, so how about something like this? Barium chloride, right? Something like that breaks up. So there you go. That's why. All right, let's try a couple problems with Raoults Law and see if we can calculate them out. All right, so we've got this pressure, and we're going to work out this problem. So what we need to do is get the mole fraction. So let's find number of moles. So I've got 158 grams of sucrose, and I know that 1 mole of sucrose happens to weigh 342.3 grams. Okay, so that gives me 0.462 moles. Okay, now how many grams of water? I've got 643.5 grams of water, and 1 mole of water weighs 18.01 grams, and that equals 35.7 moles. So then the mole fraction is going to equal 35.7 moles over 36.162 moles. Right, that's the total. Now again, look at this. This is the solvent. What's my solvent? So it's the mole fraction of the solvent. That's why I've put the number of moles of water on top. So when I take those two numbers and I work that out, I get 0.987 is the mole fraction right there. Okay, so I'm going to use that number and plug that in there. And let me just do a quick erase. Get this out of the way. Erase this stuff out of there. Okay, and so I'm trying to find the vapor pressure of the solution, right? And so I'll put my equal sign here, and I'll put 0.987, and then I've got to times the pressure times the solvent. Well, what's the pressure of the solvent? Well, it tells you right here at 25 degrees Celsius, which happens to be what we're doing this problem, is 23.8 torr. So times 23.8 torr, and when we work that, we get a value of 23.5 torr. So we can see here by adding a little bit of sucrose, right, we are lowering the vapor pressure from 23.8 down to 23.5. Not very much, right? But the important point is that by adding particles, we did do that. So let's try another one. Alright, so to do this problem, I've got two pieces of information. I've got this information right here that tells me the vapor pressure of the solution. And from the previous problem, this one right here, I've got that the vapor pressure of water is 23.8 torr. So we're going to use that piece of information to work this out. So the vapor pressure of the solution is 19.6 torr. And then this 23.8 torr should give me the mole fraction of the water. And when I work that out, I get 0.824. Okay? Now here's the thing that's important. This is the mole fraction of water. Right? That's the mole fraction of water. We use the pressure of the water as a solvent and the pressure of the solution. What they want to know is the vapor pressure of, or the mole fraction of salt. Right? So this is where we got to be kind of clever. We got to think about this. Remember that the mole fraction, no matter what they are, they have to add up to 1, right? They have to add up to 1. All the pieces have to add up to 1. So if I think about it like that, and I take my 0.824 as the mole fraction of water, if I subtract that from 1 minus 0.824, if I subtract that from 1, I get a mole fraction for salt to be 0.176. However, are we done here? And this is where we get the little glitch that makes it an AP problem versus just a normal problem. Remember that when NaCl breaks up into water, we're getting an Na plus and a Cl minus, right? We're getting 2 for 1. So this vapor pressure lowering is due to twice as many things as we think we have. So what I really got to do is divide this by 2 to get the mole fraction of NaCl. Because we don't have one NaCl floating around. We really have twice as many. One from the sodium and one from the chlorine. I hope that makes sense. I know it probably sounds a little weird, but you really got to think about what's going on. And remember, this vapor pressure lowering is due to how many particles. And when you dump in a salt crystal, you're getting a 2-for-1 molar ratio. So when I work that out, I get this answer right here, 0.882. And that's the answer. Nice little twist. Love that problem. We'll do a number of these in class. So if you have any questions about this, I'll see you next time, and good luck with it.